Good morning, dear ladies and gentlemen. I will talk about nearly zero energy buildings in multifamily building construction. As you probably know, we have EPBD directive which prescribed obligation about nearly zero energy buildings, which will come in force by the end of the year 2020. Before that, all member states had prepared the action plans for construction of early nearly zero energy buildings. And based on experiences gained in these years, we had the opportunity to test several technical concepts for construction of high energy performance buildings that are about to meet NZEB energy performance levels. In reality, member states concluded that there are certain barriers for better penetration of nearly zero energy buildings. These barriers are mainly caused because of the currently existing gap in the life cycle costs of NZEB buildings comparing to regular buildings. To say in a simple way, nearly zero energy buildings at the moment are still a little bit more expensive, speaking in 30 years time period. The next problem is that normally those buildings require a little bit higher initial investment. And in addition to that, we also face the lack of trust to nearly zero energy buildings among end users, mainly because of the complexity of the systems and technologies installed in such buildings, and some people do not like that. To investigate those barriers, we are cooperating in H2020 project NZEBs, which is about reduction of cost of nearly zero energy buildings and removing the barriers for better penetration of such buildings. We are addressing different cost reduction opportunities, and we are also investigating the attitude of end users, either tenants or owners in NZEB multifamily buildings. In the projects, there are 4 participating countries, Denmark, Germany, Italy, and Slovenia. And what is also interesting is the cooperation between research partners and housing associations, housing companies that have a lot of experience out of construction of multifamily housing in last years. About NZEB technical definition. Technical definition is a country-specific issue. We know, according to EPBD, that nearly zero energy building must have low energy demand, and that we must guarantee that this energy demand is covered prevailingly by renewable energy sources on site or nearby the area of the construction site. But in reality, how this looks in participating countries, how those minimum requirements look like. In Denmark, for instance, multifamily buildings are all equipped with mechanical ventilation, with heat recovery, and they also require the very low primary energy for covering of all energy demand. But at the moment, they claim that the renewable energy supply in those houses will be subject to cost effectiveness. It means that if it pays off, they use renewables. If it doesn't, they follow other sources. In Germany, they discussed a lot what nearly zero energy building definition will be like. In principle, they opted for at least 27% lower primary energy in such building comparing to the minimum requirements, and also for at least 30% bigger insulation of the external thermal envelope. But the final conclusion is still on the way and is still the subject of discussion on payback period and cost effectiveness. In Italy, most of such buildings have a well-insulated envelope, and they must reach at least 50% coverage with renewables. In Slovenia, we have a preliminary technical definition which requires maximum primary energy in about 80 kilowatt hours per square meter per year, minimum 50% coverage with renewables, and also limited energy need for heating. Our scope is to look for alternative NZEB solutions, the solutions that will reflect in a little bit lower investment cost and in a little bit lower life cycle cost, and at the same time will still be so-called NZEB-like buildings. In our research, we had the following research questions. Which strategies at design and at construction process can reduce the cost of multifamily nearly zero energy buildings? So let me briefly explain what kind of solutions we investigated. For instance, construction such houses out of large autoclave concrete blocks. In Italy, they reported they reduced, they reached 48% time saving for construction of external walls. And when they used monoblock windows, they saved 20% on costs and 60% on time of construction. In Denmark, they tested the construction of such houses with roof-integrated photovoltaic panels instead of classic roof with PV panels added on top of that. 28% cost savings were reached. In Germany, they searched for architectural solutions. They concluded that constructing social housing with external staircases is much cheaper. And for instance, to go for very compact surface to volume ratio that also reduces the energy cost and reduces the investment cost. For instance, if we reduce surface to volume value by 0.1, then they reported 20% energy saving and cost savings between 40 to 80 euro per square meter of construction flat. In Slovenia, we investigated construction with wooden prefabricated cross-laminated panels, which resulted in 70% time savings, which also has influence on lower construction costs. How we can improve the construction design and construction process? There are big expectations out of beam-supported design and about introducing quality assurance protocols in construction of nearly zero energy buildings. The second part is which solution sets of market-ready technologies can fulfill the emerging national nearly zero energy building requirements, of course with lower costs comparing to mainstream NZEB applications. So which technologies can reduce costs? Technologies on building envelope, service systems, ventilation, and technologies in combination with renewable energy sources. So what we did is we prepared a number of alternative energy concepts for multifamily buildings. If we start with minimum energy performance as a building supplied with district heating, double glazed windows, and ventilated with balanced ventilation driven by humidity in the living space, then we developed those energy concepts with towards heat pumps, towards combination with PV panels, triple glazing, better air tightness, and of course the heat recovery in ventilation. If we compare the investment costs, the difference in investment costs comparing to minimum energy performance, the typical NZEB buildings is quite expensive, quite more expensive comparing to standard solutions. But there are other combinations that are cheaper. This one, on top, is beyond NZEB energy concept, which also includes the use of ecological insulation materials. What about the life cycle costs? We concluded that typical NZEB buildings is much more expensive than minimum energy performance buildings. But our alternative solutions, they are cheaper. So actually we can find cheaper solutions than the ones that were most frequently used in the last maybe 4 to 5 years. About life cycle analysis and life cycle impact, we can conclude that the global warming potential in alternative solution is better comparing to standard solution and better comparing to nearly zero energy buildings. And the third problem I try to present to you is the attitude of end users. By understanding the doubts and fears and the opinion on end users about living and planning to live in nearly zero energy buildings, then if we understand this, then we can design the information campaigns for better acceptance of nearly zero energy buildings. How we approach to this issue? We prepared a questionary which focus on questions like what is important for you as an apartment user, what do you think, which technologies characterized most nearly zero energy buildings, what would be or what were your decision triggers for living or moving into NZEB buildings. Altogether, we provided almost 300 responses of the end users from 4 countries. And here are some interesting results. For instance, for Slovenia, the question which technologies characterized most nearly zero energy buildings. In Slovenia, end users think that the most important and the most relevant for having an NZEB is to have good air tightness, then to have triple glazing, high thickness of insulation, mechanical ventilation with heat recovery, good appliances, A++, and also good architectural concept. And after that comes renewables and energy efficient systems. One more interesting fact is that 32% of potential future NZEB users expect bigger maintenance costs in such buildings. But in reality, 71% of current NZEB users claim that they actually don't experience bigger costs. Results for Germany, for instance. What is important for German multifamily building users? Mostly they are tenants in such buildings. So they think that low costs for rent, energy, and maintenance are important, low energy consumption, and also healthy building materials and good access to the daylight. If we compare between the countries, then we can say that the perception of technologies that characterize nearly zero energy buildings explained by potential future users of nearly zero energy buildings is like that. In Italy, the most characterizing technologies are considered to be solar collectors, photovoltaic panels, renewables, smart technologies, A++ appliances, LED lighting, while in Germany, nearly zero energy buildings is associated with triple glazing, good insulation, envelope, airtightness, and mechanical ventilation. Another issue, opinion on current energy, nearly zero energy building users on importance of certain expectations in their flats. Slovenian NZEB users, for them the most important are low investment costs, low energy costs, fresh indoor air, and good thermal comfort. And on the other hand, for Danish NZEB users, the fresh indoor air has a little bit low priority, which does not necessarily mean that they don't care about it, but they probably have this for granted because they already have they already use mechanical ventilation with heat recovery. To conclude, the survey addressed end users' concerns and doubts about living in NZEB buildings, and those doubts are in general connected to indoor air quality, especially dry air in the winter, and the doubts were related to longevity of advanced materials and lifetime good performance of technical building systems in nearly zero energy buildings, about the user friendliness of control systems and ICT appliances in the building, and about the cost benefit of numerous technologies and their actual usefulness. So this is the opinion of the users. The challenges in construction of multifamily nearly zero energy buildings in Slovenia are to reduce NZEB investment costs by alternative solution sets in order to make these buildings more competitive and to facilitate NZEB market. The challenge is to introduce experienced designers into the process, to engage skilled construction teams, and to introduce quality assurance protocols in construction process. The challenge is to optimize the costs and environmental impact over the whole life cycle of such buildings, to increase end-user acceptance by sharing tenants and owners' best practice in living in NZEBs, and by dispelling the myths about living in such buildings. And finally, to provide feedback to policymakers regarding user-friendly NZEB buildings regulation, which is about to be put in place by the end of the year 2020. Thank you.
Thank you. I would like to ask, this is the last presentation. about the limit of these nearly zero energy buildings, about this 80 kilowatt hours per square meter in Slovenia. What is everything calculated inside of this value?
In this value, EPBD energy use is considered. It means that heating, cooling, ventilation, domestic hot water, and also basic use of electricity for the systems, not for appliances and not for elevators and such things. This is according to EPBD methodology. And all those figures about primary energy between the countries, the issue is that they cannot be easily compared. We have to be aware of that because conversion factors for calculation of primary energy, they strongly depend on the national energy situation. So if I mentioned 20 kilowatt hours primary energy in Denmark and 80 in Slovenia, we have to know that in Denmark, for instance, for the district heating system, in average, the conversion factor is 0.6, while in Slovenia is between 1 and 1.2. So this is generating big differences, and we have to understand this primary energy information as a very national dependent.
Okay, but mostly the energy is for heating, is using, this is a big percentage of the energy. And we know that for passive buildings are 15 kilowatt hours per square meter. So this is big difference between 15 and 80.
Those are not the same figures to compare. First of all, I would say that in buildings, in high-performance buildings, space heating is not any more prevailing field for energy use. So hot water is also very important, sometimes even more important than just heating. Passive houses, they have the 15 kilowatt hours per square meter in passive house is only energy demand for heating. This is not primary energy. In passive house, in German definition of passive house, the primary energy is limited to 120